When you get the biggest applause for making your laptop work, it's, something's gone wrong. Okay, this is me. I won't waste any more time covering that. After that fantastic warm-up. It didn't say ray gun just because I like ray guns or anything like that. It's the company I finished working for recently. So this talk is going to try and combine a couple of things. I like digging into the internals of the .NET Runtime. I blog about it. I spend time. The source code of the runtime has been available for a few years now, so you can dig in, you can compile your own version of the Core CLR runtime. There's lots of fantastic docs and other things to explain. I love figuring that stuff out, because for me it's really interesting to find out. But maybe a bit more of a justification is actually the idea of understanding one level lower than our usual abstraction. Now, I'm not going to claim that day in, day out, we're all worrying about the intimate details of the runtime. We might be up in ASP.NET, we might be worrying about what's going on in the base class libraries, but there's always times, isn't there, where we need to drop down, and that's, pretty much what this entire conference is focused about, is those low-level details, because so often you need to know those low-level details if you're going to worry about performance. You need to understand what's going on in the GC if you care about GC performance, and minimizing pauses. You need to understand what the jitter is doing if you want to see efficient code, and there's going to be talks later on today that's going to touch on all these areas. So this is kind of my justification for doing this sort of talk, is actually, I think it's good for us to know, we're not all of us all the time, every day, day in, day out, are going to need to know the things in this talk. I won't claim that you'll be able to take stuff from this talk and go away and change your code base on Monday. But I think it's good to have this knowledge, and people seem to like to have this knowledge of what's going on under the hood in the internals of the runtime. I've tried to mix two things together. So there's a lot of things that go on in the runtime. I've done a talk before which is telling you about everything that happens from the point you type .NET Run to the point that Hello World is displayed on the screen. That's a 45-minute talk just covering that. So there's loads of things going on there. We might not even realize some of those things. But I've tried to find the intersection of what the runtime does to make performance, or to give us really good performance, or to provide really low-level performance. And if you think about the runtime, it has to handle every scenario. The runtime provides us with a way to do something as simple as a method call, all the way up to the complexity of the GC. So when we're talking about performance in the runtime, we're talking about low-level, and there's a justification in the runtime for something that happens a lot, say a method call. That's quite ubiquitous. We can't write very much code without doing method calls, to tune that really excessively. So when we're talking about performance in the runtime, it's quite low-level performance. There's quite a lot going on. Before we get into that, I'm just going to do a brief overview of what the runtime is, what it contains. Here's some stats. It's from about a year and a half ago, so they've probably increased somewhat by now, but we're talking about 2.5 million lines of source code in there. Way more than that lines of test code. So the bulk of the C# code in the runtime is tests. There is a section of the runtime that is C# code, but the core of the runtime is C, C++, and a whole sprinkling of assembly code for the per CPU architecture stuff. There's a bit of IL code in there because they're obviously trying to test fairly low-level parts of the runtime that you maybe can't even express sometimes in high-level languages. And I have no idea why there's Python and Perl. I think it's build scripts and other bits going on right down there at the bottom. But this is to give you an impression that this is a serious bit of engineering. The Core CLR repository, that's the open source one, appeared publicly a few years back, but that's come from the heritage of the .NET framework and Silverlight and all the other .NET runtimes over the years, so it's built on top of that. It's not just appeared in isolation, so you're getting on for 20 plus years now of work that's gone into the runtime. This is what it looks like a bit more visually. This is the blocks of this represent the top-level folders in the source code. They also represent the terminology, so the JIT, the VM is a virtual machine, SOS you might know, GC, some of these phrases might be familiar, but the size of the blocks is just a number of lines of code. So I'm not saying complexity, some parts are more complex, but a few lines of code, but it just gives you a rough idea of how things are divided up. And you start to see per CPU folders going on there, i386, AMD 64, and so on. Let's dig into a few really quickly. MS-corelib is a bit out of date. It's been renamed to system.private.corelib, but this is the C# code in the runtime. and that's the code that gives us the APIs like system.gc. Anything that's in the runtime but needs to be controlled from C#, the API will live in here because they obviously need to be tied together. So the system.gc is a really good example. That has to also, there's a rule in the runtime, it has to be self-contained. The runtime can't reference anything else. So any code that code needs to be pulled into there. It can't have a reference on an external dependency, this C# code, so that the runtime can be self-contained. The JIT is the just-in-time compiler. A whole lot of complexity in there. That's the part that does the work of turning our IL code that we've produced in the Roslyn compiler, Visual Studio, VS Code, whatever it might be, turning that into machine code that can be run at runtime. There's huge parts of that worry about the different CPU architectures. There's parts that do the parsing of the code into sort of syntax trees, those sorts of things. There's a lot going on in the JIT compiler. And that's one of the areas where we get a lot of performance. The code it produces is trying to produce the most efficient code to run on the CPU we're running on and make our code run as fast as possible. GC is, I'm not going to cover that. There's people way more qualified than me to talk about the GC. The fun part about this is that whole block is basically one file, pretty much of 35,000 lines of code. gc.cpp, certainly in Chrome. If you go and look at it on GitHub, it refuses to render the file. It's too big. It says, download the raw one. You can speak to Peter and some other people if you want to learn about some of the history about why that file's as big as it is. But it's, they understand the code. It's fun to look around. But there's someone who's written a 1,000-page book who can probably explain a little bit more as well if you want to know about that. This is the parts of the runtime. So SOS, people have heard of SOS, yeah? For debugging, WinDBG, use the SOS, Son of Strike. It's the part of the runtime that lets external things dig into the parts you need to debug. So a debugger on its own, a native debugger won't understand the managed runtime. So this is kind of that layer. And there's also in the top right-hand corner there, the data access layer, which says, given a .NET process, tell me about it. How many threads are running in there? Where's the heap? How big's the heap? That's the layer that maps between the two. The point of showing this is really to show there's a lot of code in the runtime to make debugging, diagnostics, memory dumps, all those sorts of things possible. The runtime provides that. Visual Studio as well has to do a whole lot of work. This is more of an API that needs to be used. So there's work on that side, but the runtime has to provide that. It's a managed runtime. It needs to provide these services. The PAL layer is the part of the runtime platform adaptation layer, and its job is to say, right, the runtime can work on different OSs, Windows, Linux, and so on, and it abstracts that away. Its job is to say, right, you're doing something that's OS specific, so you can call into the PAL and it will do the job, and that's the theory behind that. A couple more, the includes bit in the middle roughly translates as the APIs the runtime uses. It's header files in C++ terms. Sometimes there's APIs between the different components, so the GC and the VM in the top left-hand corner, they talk to each other over an API, but also externally. Anyone here work on the profiling APIs, any tools that use the profiling APIs, iCore Profiler, a few people, debugging APIs, any of the runtime provides APIs so that third-party tools can use those APIs to provide the profilers that we use. Okay, and then the VM is kind of everything else left. To give a bit more specifics, here's some of the things it does. So it worries about type system. Generics is a huge part. If we compare .NET with Java, for instance, they've done that differently. There's a whole lot of work that went in to make generics work in .NET. The built-in types live in there. It deals with loading types and classes. It's got to make sure any types it needs to load don't break the rules of the type system. The managed runtime gives us a lot of guarantees about our code, and that's enforced when types are loaded. Threading's in there, exception handling, stack walking, all these complex things that we kind of take for granted, which is the whole point of a managed runtime, but there's a whole lot of complexity. Event tracing and profiling, and pinvoke and other things. So to talk about more specific parts, the first one I want to talk about is virtual stub dispatch. Anyone has heard of this in terms of the .NET runtime? Excellent. So a few people are going to learn something new today. And hopefully the ones who already know about it will learn something as well. This is the sort of probably the most common code. Has anyone got this kind of code in their code base? right? You've got an iLogger interface. Come on, I'm sure most people have got, yeah, okay. It's like probably the most common interface you might have in your code. And we use interfaces because it gives us an abstraction, right? In this case, we can program to the interface of the iLogger, and we don't care whether it's a console logger or a Azure storage blob logger or whatever other types of loggers we might have. We just pass around the iLogger interface. We know that there's methods available on it, and it just gets on and does it for us. And we might kind of take that functionality for granted. I'm sure if you haven't got this interface, I'm sure everyone here is working on a code base that has interfaces in there somewhere. It's pretty standard to use interfaces, even with one implementation, so that we can swap it out for unit testing and mock it and those sorts of things. So they're ubiquitous, and calling methods via interfaces as opposed to via concrete classes is pretty standard. But why is it called virtual stub dispatch? Well, we don't use the virtual keyword in this scenario, but if you were to look at the IL, so the green comments there are .peak will decompile your code into the IL. So we see the virtual is showing up here. And another way I think about is virtual is basically the target of the method can't be determined at compile time. It has to be figured out at runtime. So you have some code. You might use your interface in something like this. I mean, maybe with some slightly better method names, but anyway, this is a good kind of general idea. We pass around an iLogger interface. It might come from dependency injection. We might not even new it up. It might be magically done by some config settings or however we do it. But we have these two methods, and we're really looking at the example here of the iLogger. So the something went wrong method, all it has is an interface. And for that to be figured out, it doesn't know really where that interface comes from. Now, this is a fairly simple example because it's newed up the object just before it's passed it into the method. So there's a chance that the JIT can figure that out, or it might even inline it in this exact example. But generally, your object's created somewhere over here and it's used somewhere else in your code base. And the JIT doesn't or can't do that huge complexity to look at everything. And also in .NET, there's a lot of ways to dynamically load things at runtime. We can load new DLLs, assembly.load. We can emit IL dynamically. So there's not really a way for it to say, well, I know exactly which interface, sorry, I know exactly which concrete class you're talking about here at compile time, because that analysis would be tricky. Even at JIT time, it has to actually be figured out at the time the method runs at runtime. So if you're people familiar with IL code, you might have seen this before. It uses the callVirt instruction, callVirtual, and the compiler basically says, so this would be what the Roslyn C# compiler would produce. It says, I want you to call the log error method on the iLogger interface. It's a bit more blurred now because we have default interface methods, but you can't call a method on an interface generally, right? And this has been around for a lot longer than C#8, where we've had the ability to add methods to interfaces. So it's saying, the compiler's basically saying to the runtime, I'm going to let you figure this out. It's the call virtual instruction. And there's a call instruction if it knows the exact place it wants to go to. Because when we get to code being executed at runtime after it's been through the JIT compiler, there's not really the concept of interfaces. It needs to know the exact exact location in memory to a memory address of where that method exists, because it basically needs to do an assembly instruction to call over there or jump to that location. So it needs to have something more concrete. All the abstractions built in by the compilers and provided by the runtime are higher level. But ultimately, when it gets down to it, we're running assembly code on a CPU. So we talked about why it's virtual. Now, stubs. Stubs are something that show up in the runtime in a whole lot of places. If you've got a spare 30 minutes and you want to read about every single example of stubs in the runtime, there's an 11,000-word blog post there that if you're really keen, you can read. It's got a table of contents, so you can find the bits that interest you. But they show up in a lot of places in the runtime, and they roughly look like this. You have the call site on the left, which is the code that is calling a method. So back in our example where we call the something went wrong method, that's the call site. And the callee is the method where it's being executed that we want next. And there's a whole lot of stuff that actually goes on in between. Even without stubs, the JIT compiler figures out how the arguments are passed into the method. There's some rules about that, and that varies per CPU. There's conventions, and it's known as ABI, application binary interfaces, and it has to fit with that. But the stub sits in the middle, and I like to think of it as doing a bit of tidy up work, a bit of fix-up work. It can do whatever it feels like. It's often we're talking a few assembly instructions here when we're talking about stubs. They're very tailored to the exact scenario, very performance critical because they appear in so many places. And this is all contained within one single method call. The second half where we transition from the stub to the callee is often a jump CPU instruction. It's not a full method call again, so don't think of this as two method calls. This is at a much lower level. So this is from the LinkedIn page of a guy called Simon Hall, a colleague of Peter's. I was just chatting to him about it. He's on, the only reason I know about him is he wrote the book of the runtime page, and I'll show you some links later, but it's some pages written by the runtime engineers. But he's talking about the work he did to make something as simple as when we're calling a method via an interface in the code I just showed you. That got overhauled in .NET 2, so he's obviously very proud of it. I mean, you would be. It's a pretty fundamental part of the runtime, and he put it on his LinkedIn profile. But it's describing exactly what they did. They redesigned it, interface, dynamically generated stubs, and it led to an increase. Because something as common as calling a method via an interface, we want to be quick, right? We probably didn't even think that there's a big issue between calling it with an interface versus calling it directly. We just do it in our code, and that's great. That's part of what a runtime should provide. We shouldn't have to worry about being more complex or being more less performant. And that's part of what the runtime does, and they managed to do it, led to an increase, a better memory usage, and certainly improved the throughput. That's part of why they were doing it from the old way it was done previously. What does that look like? So there's actually 4 stubs involved here to give you a bit of the idea of the complexity. The first one is the basically I don't know stub. It's like, I don't know where you want to go. I need to figure that out. I need to look at the method you're trying to call. I need to look at the object you're calling it against and work out the exact location. That's doing, looking for a cache and saying, right, what's the actual we're talking about memory addresses at this point. What's the location in memory I need to jump to find the implementation? So in our case, we're talking about the iLogger interface, and it might be going to the console logger or whatever. We need to find that method. So it starts with there, and obviously the first time it doesn't know that, so it goes down to a generic resolver. That's a bunch of C++ code, and that does the heavy work of populating the cache and saying, right, this is the location in memory, this is where the interfaces for this class are implemented. But there's kind of another few scenarios. So I don't know if anyone's heard of the terms monomorphic, polymorphic. The idea is that actually, a lot of time, we might only have one class that influence an interface. Basically, if we're being good with our unit testing, we'd often abstract even a single class behind an interface. In our production, the code that's running in production, we would only have one implementation of that interface. Maybe in our test code, we have another one, or we mock it, or whatever. So there's that kind of case. And this is the work the stubs do, because it optimizes for that case, saying basically, I know really there's only one. Anytime you call via this interface, you're really going to only end up at one place, so I'm going to optimize for that. But that might not always be true. It might look like that's true in the first place, but we're talking about dynamic code. Code can change. We're talking about call paths in code bases. We're talking about methods being called from different places in the code. So sometimes it has to fall back to the polymorphic, 2 or more, and it has to do the work out there. What that looks like visually, and this is from the book of the runtime. Have people heard of the book of the runtime before? A few people? Yeah. So if you want to start to understand what's going on in the .NET Runtime, the book of the runtime, the URL's there, BOTR. It's pages written by the .NET Runtime engineers for other .NET Runtime engineers. So I personally have to read it about 5 times before it makes sense to me. But the idea is that it's talking about the low-level details. And the fact that virtual stub dispatch has its own page kind of gives you an indication it's fairly complex. But we can see the stubs I just talked about there. An indirect cell, and it uses something called backpatching, where it rewrites the indirect cell to point to the different one, and there's all the different flows, and the page explains all the different ways you can follow the different arrows, and there's a lot of complexity as you move between the states. To give you an example of the simplest one, the monomorphic single case, one thing aside, you might have multiple places in your code that call into the same method, so you have multiple call sites method, and they can have different dispatch stubs, because the idea is actually in call site 1 you might be calling it in a particular way, in call site 2 another way. So they've tailored the stubs to be specific to the call site, again to give high performance, so it can actually behave differently even if you're calling your method from different places. And this is what it is. I'm not going to show a lot of assembly code in this talk, but even for me, who doesn't really understand assembly code, I can understand compare, jump not equal, and jump. So this is, we're talking about the caller on the left, which is starting off the method call. And this is a single case, and it says, I'm going to make the assumption that the method you called last time, the type, so the expected MT is method table. Method table is a data structure in the runtime that describes a single, what we would call a single class or a strut, a type, a single type. And each object on the heap has a method table pointer attached to it. So for every single object, that's part of the overhead that you get on objects in .NET. And they point to this method table. And that says basically, if it's comparing against that, it knows it's the same object that it saw last time. And it knows for the same object that it's going to dispatch the same way because that object will implement the interface in the same place. So it's optimizing for that path. It's doing a simple compare instruction, and if that works, then it goes straight to the target. If it isn't the same as last time, remember we're talking code that can change here. We're talking in particular call site. It has to fall back to the failure mode. And I'm not going to go through all the modes because there's a whole lot more assembly code involved. But I just want to give a sense of the work that goes in to making something simple as a method call fast and performant as it can be in the runtime. Having said all that, there's work ahead to de-virtualize. So we talked that this is virtual method calls. As I explained, it means it has to be figured out at runtime. There's still an overhead. These stubs, even 3 assembly instructions, the fastest case we just showed there, that's still an overhead, and it's also an indirection. You're jumping over here in memory maybe, and then jumping back to your actual methods. You're having to move around. That costs. If you're talking, millions of requests per second, that can start to be a cost. So sometimes we'd actually like to not have virtual method calls. We'd like to have de-virtualized in effect. And there's work done in the runtime. You can see a couple of ones have been done. So de-virtualized interface calls that we talked about when you do virtual calls on structs as well. But there's still a few other places, well, a few. There's still quite a lot of that list to complete before. And the idea is that JIT can do a bit more analysis and say, actually, I don't need to fall back to this stub at runtime. I can do a bit more analysis. I can say, definitely, you're going over here. And in that issue, it links to a doc that's going to design doc, if you want to read more about that explains some of the techniques they may use in the future. But it's being worked on again. We can have good. We can be comfortable to know that the runtime engineers have got our back on this, right? We want to just use interfaces. We don't want to care about this. We just like to know that it's fast and performant. Okay, on to saying value types. Everyone here has heard of value types, right? I think it's impossible to have a .NET, a job working as a .NET developer and not be asked about value types in an interview at some point in your career, right? Everyone's had this question. Value types versus reference types, stack versus heap, all this sort of stuff, right? So I think we're familiar. I'm not going to do an intro to that, other than to say there's a few things that they do give us in terms of performance. One is we don't have this, I talked before about this method table. Value types don't have this extra method table. That's part of what limits them. It's why you can't have, implement, you can't base classes and things like that in structs because we don't have the ability to look into the method table and work out the hierarchy and things like that. So a value type, you get just the data that is in your struct. If you have 2 fields, the size of it is just that, aside from sometimes there's padding for low-level reasons, but generally it's just represented by the data there. It also packs in more, particularly if you start to put struts in arrays. An array of struts is just literally the size of the struts. An array of reference types, classes, is an array of pointers, in effect, that then point over to the data that lives somewhere else. So there's performance gains there. And they allocated on the stack, except when they aren't, if you know the answer to the interview question. It's not guaranteed that value types will always be on the stack. If a value type is inside a class, then it lives with the class on the heap. So there's some caveats there. But the reason that allocating on the stack is beneficial is because the GC doesn't have to get involved. And I have to be very careful. There's a few talks about GC. Not to denigrate it, it's a fantastic bit of engineering. It does a great job. But it's quicker if it doesn't have to do a great job, right? So being able to have our code, our data on the stack is advantageous because there's no work for the GC very little work for the GC. It certainly doesn't have to worry about cleaning it up because that stack is just moved back up as we exit the method. So, to give you an idea, if you search for isValueType, which is a method on the method table class I've talked about before, in the source code, there's 64 places that does that. So it's pretty widespread, right? There's a lot of places in the runtime need to care about whether the type you're using is a value type or the opposite is not a value type, a class, an object. And that thing, you can see some of them there. We're talking about in arrays, it worries about it. Reflection, clearly the debugger needs to know. They look different in memory. The JIT certainly needs to know. It needs to do different things that we'll talk about in a moment. So there's a lot of work going on in the runtime to make value types possible. We just literally have to change one word. We have to change class to struct in our code, right? That's fairly simple. But that has pretty big implications for what the runtime, how the runtime treats that code. To give you an idea, this is about as low as I'm going with CPU registers and things like that. This is from an actual issue on Core CLR, and it's involving calling delegates. And there's a fantastic, one of my favourite stubs. You see the shuffle that shows up, and you can read that to see about it. But the point is that reference types are always a pointer sized, right? They're 32-bit, 64-bit, so they fit in a single here. So we're talking about registers when they start with an R. On there, or stack slots. And this is what our arguments go into when we call a method. Again, it's one of those things we kind of take for granted. We just call the method passing the parameters. But at the low level, the JIT and other parts are worrying about registers. And registers are more efficient, so it tries to put stuff, that's why it starts with the registers. But the point is, in here, we have this is a real-world example, that's why I used it. So we have struts here. E and F are struts with 2 and 3 fields, A, B, and C, and A, B. And you can see in the two examples, it's had to worry about, in the first case, so what basically is happening is we're moving out to this point, so that's why they're shuffling. You can read the issue for why that happens with delegates, it's not general. But the point is in the first case, they're all in stack slots, all start with an S. In the second case, 2 of them end up in registers. So this is just some of the complexity the runtime has to worry about. Because struts are passed by value, it needs to fit the entire contents of the struts fields. That's why, in this case, A, B, C, and D are reference types, so there's just one slot for each one register. But once it gets to value types, it needs to worry about fitting them in. And there's certain rules about whether they can be split between registers and stacks. They can't. That's why it has to do more work, and that's why it's done things differently here. It tries to use registers. There's all sort of different rules. And this varies per CPU. So this is talking about Unix x64. It would be different on Windows x64, just for fun, because they have different conventions. It's obviously different for ARM and ARM64 and x86. So there's like 5 times the complexity because the JIT has to do different things in every single time. So even just passing a value type, a struct, into a method, there's a whole bunch of work the JIT has to worry about to make that happen. But on to another case. Once you start to see these features interact, it gets even more complicated. So when you use generics and value types, things get more complicated. So probably people might have heard that generics in .NET use something often referred to as like shared generics. When you have a method like this, a store method, when T is a reference type, there's only one version of that method generated by the JIT for every reference type. As I talked about before, reference types are the same size on a particular 32-bit or 64-bit when you're running. They point to the reference elsewhere, the data, so they don't have to do anything different, even if the classes that they're referencing to are completely different. The reference type stays the same. So that store method doesn't need to change. So it generates one version of that method. And that's an optimization, because otherwise there'd be a code explosion, right? There'd be loads of these methods in memory. Every time we instantiated this wrapper for, where T, if we did a generic wrapper of my class, your class, everybody's class, right? Every single time there'd be new versions. So the runtime does a nice optimization to share it for reference types. But it can't do that for value types, even the simplest ints and doubles, let alone our own struts, because they're different sizes. And even if they were the same size, you start to worry about different CPU instructions for ints and doubles. So in this case, they're different sizes, but you can see they're using, you've got the V, move, SD, versus a regular move. So even something as simple as just storing, this is the code to store a value in a field, has to be slightly different when you do it with an int and a double. And it's clearly even more different when you have struts that are, your own ones made up of multiple fields and things like that. So it has to do a bit more work. Again, the runtime's got our back on this. It just does it. We don't really care about it. too much. But a nice side effect to this, I don't know if it was deliberate. I think the deliberate part was to reduce the size. You couldn't do the same optimization for value types as reference type because they are different sizes in memory. They worry about different CPU instructions. But a nice side effect is actually you can use it as a performance optimization. So people have heard of the Kestrel web server. It's the one that's come out in .NET Core. It's the one that's making .NET look great in the Tech Empower web benchmarks. Running it, we're talking tens of millions of requests per second. It's up there near the top of those benchmarks. And a guy called Ben Adams from the community has done a lot of contributions and some. If you want to learn some crazy performance tricks, just follow his commits on this repository, and you'll see some of this stuff. But he's using a trick where you deliberately include struct wrappers because of the fact the JIT generates different versions. So I showed a very simple one there for int and double previously. But the point is the JIT will try and generate it has to generate two method versions. It specializes for each value type. So if you wrap your code in a struct, it will specialize. And when the JIT specializes, it can make more assumptions because it knows this code is only for when this method is called, where the type is an int or a double in our previous example, or whatever the struct might be. Because of that, the JIT can make more assumptions because it knows about the size of the type or whatever it might be. It can get rid of some checks it knows will never happen because you're passing in a particular type. So you can use it. This is a real world example. You can use it to get performance benefits. He calls it, so David Fowler, I'm sure some of you will know, who's one of the architects there. He calls it out as type system abuse, working with the type system, or however you want to describe it, but it's a fairly well-known trick for high-performance situations. And as I get saying, please don't go back and say some guy at a conference told me to rewrite all my code with struct wrappers because it's faster. There's only certain situations where it really matters, but it is a performance trick that's used there. And the particular example he used here was to make that pull request was introducing a frame adapter, very similar to the code I just showed before, in fact. Literally just wraps it, but the fact it's a struct. It wraps it in a struct, and then the actual changes we're using the frame adapter, and just so you think it's doing very little work, but because it's a struct, the JIT can do the sort of optimizations we talked about before. And this added, in one of the Tech Empower benchmarks, it added around 40,000 requests per second. It was already running at 1 million plus requests per second, so that gives you kind of the relative bit. But that sort of level is a significant difference, just making this particular change. Having said all that, there's talk of moving away from that. Some bloke who didn't know what he was talking about thought he'd asked the dumb question, and that's me, by the way, at the top. And then if you've ever done any work on or seen the Core CLR repository, Jan Kotis, the engineer at the bottom, knows a lot about the runtime. But the idea is that actually sometimes you'd like to not have this specialization. It's tricky in ahead of time compilation scenarios and other things as well. So there's potential. This is an issue that came up recently in the Core CLR repository, and the idea is that actually it might be, for some scenarios, moving away from that specialized thing. I don't think it will hurt the performance benefits we see, but certainly it's going to start to be used in the tier 0 compilation, in tier compilation that we'll come on to in just a second. Another part of value types is boxing, right? It's probably the one part we're most familiar with, that certain time value types have to be turned into heap objects. Sometimes that can happen without us realizing it if you call the wrong overload of string.format. Sometimes we explicitly box because we want to put it in an object, but it's converting the value type into an object, and the runtime makes the type available. It makes the boxed version available for us that matches the struct version. But just to give you a rough idea of how complex even that simple thing we think about boxing is. So it starts off with the JIT will actually try and inline that. Inlining is the main optimization the JIT starts with, because once you inline things, it makes other stuff possible. So there's the method import and push box. That generally only works when you're boxing primitive types. It probably won't work if you're boxing your own struct. But then we start to get into fast assembly helpers. So there's a whole chunk of handwritten assembly code in the runtime that handles specific examples. So we talk about how you should avoid boxing because it puts more stress on the GC, although the GC can handle quite a lot. We don't need to treat it too carefully. It's a pretty impressive bit of engineering, so we don't have to worry too much about whether it's going to have a problem. But the point is it tries to even make the act of boxing, this is just creating a boxed object, quickly as possible. So there's handwritten and the JIT box fast, that's the multi-processor optimized version with an inline get thread call. There's a single processor version. There's ones without the inline get thread call. This is quite common in a runtime to have very optimized CPU chunk snippets of CPU code for different scenarios. And they generally will do the happy path, the quick path, and then if it falls back. I'm not going to do a tutorial on GC allocation, and there'll be plenty of stuff about that later, just to say that basically the fast path won't actually trigger a GC allocation. It then falls back to the C++ code in the JIT box method at the bottom. And it ultimately ends up in some code that looks a bit like this. And you can even see some optimizations going on here, right? So if the value type is 1, 2, 4, or 8 bytes in size, it does it via writing pointer references. It's not even really a copy. It's saying take the contents of this pointer and put it in this pointer over here. If it's not one of those, so if it's 3 or 5 or more, it does a mem copy. So ultimately copying data that's in the fields of the value type into the object that's on the heap that we're boxing into. Finally, at the very lowest level, it has to make the GC aware, right? You've created a new object that wasn't there before, and your struct may actually have references. Structs can contain fields that are references to classes, right? You can put that doesn't stop you doing the restrictions. So the GC has to know about that, otherwise the GC wouldn't know to keep that object alive or whatever. So at the lowest level, what I like about this is I'm far from a runtime engineer, but I can at least just about understand and follow this code. It's an iterator loop, right? If we're writing it in C#, it'd be a for each, but you don't kind of get that nicety in the C++. So it's it's iterating through a series of values and then doing the work each time in a loop with a simple while loop there. So don't be too scared about digging into the code in the runtime if you want to find out what's going on. The reverse process of unboxing is not done so often. You don't tend to unbox as much as you box, as in every time you box, there's no guarantee that you will unbox, so it's not quite as optimized, but the JIT still wants to inline it. And if you want to read a 5,495 line of code method, you can go and see that one there. When you're writing some of the C++ code in the runtime, there's obviously a warning built into the compiler that says this method's too long. And you can search through the code and you can see everywhere they've turned off the warning. And this is one of the classes basically saying, yeah, I know this method's too long. I don't need you telling me that. Thank you very much. So it tries again to inline it. And then it falls back to code and it will get so we're talking this is taking an object from the heap, putting it back onto the stack. So the first step is to get a pointer to the data in the object on the heap. And then it needs to push that onto the stack. Just to touched on it a little bit, but even calling a method, so if we have a foo, I ran out of good ideas for method names at this point. If we have a foo method on a class or strut, so we'd write the top line, right? And whether it's class or struts, at the method level, we don't change anything, right? But behind the scenes, there's a bit of a change. So maybe you're aware that every method call in .NET to an instance, when we're talking about an instance rather, a static method call, there's an implicit this pointer so that it can know the instance. So when it gets to the method, it's got the pointer to the object. And that's part of, object orientation and do we encapsulate our code and our data together, that sort of thing. When it comes to, with a strut, it actually would do the equivalent as if we passed a ref, the struct by reference. And if you know about the ref keyword in .NET, that's so struts are value types, they're passed by value, but when we use them in this case, if in our foo method we wanted to modify the strut, we'd want those changes to last outside. That's why it has to be passed in by reference. So even something as simple as a single method call, and there's a little bit difference going on with value types and struts. On to the last bit. So one thing you can do in value types is you can override methods, right? So you can override toString or whatever. If you had a strut like this, and it ended up boxed, you could still call the toString method, right? It's one of the methods on system.object. You'd expect your version to be called on the struts, wouldn't you? You wouldn't expect it to call the one on object when it had been boxed. You'd like it to come back to this one because you've written your own version. And that's something the runtime makes available to us. And it has to use something called an unboxing stub. So our struts, we talked about before, struts are just the data in memory. There's no extra things. So our struts might look like this. It's got a few fields. One of them set to hex value of 5. When it gets boxed, the process we just went through with the code, it ends up looking like this. So we have the object header, the method table that I've touched on a few times, which is a pointer to the data structure that describes the type that the struct is. And then the actual data fixed there at the end. And that's why one of the main benefits of struct is you don't have that extra overhead. It looks worse in this scenario. Obviously, the bigger your struct, the less the overhead makes a difference. But if you know about how .NET pointers and this pointers and stuff, in .NET, the pointer of the object is to the start of the method table. And offset behind that, you have the object header. And the idea is the method table is the bit you want most of the time because it describes it. So that's where this pointer ends up pointing. But when you box it, the strut, it has to adjust it because by the time it calls the toString method that we saw in the previous slide, to make that method be the same, whether it's being called on the box version or the struct version, it needs to be able to make assumptions about where it can find the fields of the struct that it's living in. So a stub sits in there, and the stub's job is to literally move that pointer. If you remember back to that diagram of stubs, it would sit in the box in the middle, and it would just adjust the pointer so that by the time the method called, it's in the right place. So again, this is not a like you need to know this to use struts, but I think it gives you a good appreciation of just how much work goes into making value types. We just merely, like I said, change class to strut and deal with the differences about by value, by reference, but there's a whole lot going on there to make that possible. On to the final part of performance optimizations in the runtime. I like this one because all the ones I've talked about before, value types have been in .NET Runtime since the beginning, since 1.0. The virtual stub dispatch that I described earlier has been there since 2.0. So a lot of these internals don't fundamentally change very often, right? They've been baked in since the beginning. They might be tweaked, they might be improved, but they've been around for the runtime for a while. But tier compilation is quite new. So have people heard of it before? A few people, excellent. Okay, so it's shown up in some of the .NET Core versions. It's now available. It's turned on by default in .NET Core 3. So I think people are going to hear about it more. And what it's trying to achieve is, one of the issues with JIT compilation is that it's just in time, right? It's in the name. We can't execute, our code won't run until the JIT has done its job of generating the native code from the IL. And that sometimes becomes an issue on startup because you have a kind of cascade effect. Method A equals method B equals method C. And they all have to be JITted before the final method at the bottom of the call stack can actually run. So it is just in time. It will not JIT the code until you actually call it. But on startup, you can see sometimes you can see excessive time spent in JIT compilation. And there's various things. People have heard of NGen and other things like that, maybe. There's various things being done to try and improve that by pre-compiling it so you don't do it on program startup. You have a cache. Tier compilation is trying to help that as well. And the basic idea says that rather than just have one go, that's the other fundamental thing about JIT compilation. It's only had one chance at JITting a method, and from that point onwards, the method just runs. Tier compilation is we're going to break that dependency and we'll have 2 goes. We'll do the tier 0, it's known as. We'll do the compilation as quickly as possible. We won't do very much optimizations. We'll get the code out there as quickly as possible. That helps decrease startup time because the JIT isn't spending as long time, because all these optimizations take more analysis in the JIT compiler. It has to check more things, it has to analyze all these sorts of things. It doesn't come for free. So it says we'll do the minimum optimizations first, we'll get the method out there, it's native code, it's running, but it's not the fully optimized version. And the assumption is that actually you don't need to fully optimize every single method. If your method runs once a day and it takes 10 milliseconds rather than 5, that's probably no big issue. If your method runs 1,000 times a second and it takes 10 milliseconds rather than 5, you've got a problem, right? So it's saying actually rather than just do it once and try and get the best version, we'll do a simple version first and then we'll count the methods. And once we know the method is hot as in being used a lot, being run a lot. We'll have another go in the background, and we'll recompile it with a full optimization, so we can take a lot longer, relatively a lot longer, because it's not blocking the method being executed. So that's what tier compilation gives us. It looks a little bit like this. So again, stubs, I told you stubs are everywhere. Every time the method is jitted in our code, it goes via a stub to make that possible. This is what it looks like before it's jitted. So this stub is put in place. We end up in this temporary entry point. It goes through a few layers, and the pre-stub worker is some C++ code that does the heavy work. That might call into the JIT. It might put another stub in. There's a few things it can do there. After jitting, we end up with the native code. That's the method that can run. We still go through potentially an extra level of indirection, because if our method is a virtual stub dispatch that we talked about before, that stub is still there. There's also a stable entry point that we can go straight to the native code. There's different scenarios where those things apply, but the point is we're no longer going through the pre-stub. We're no longer doing this. So this is done once. The JIT's done its work. It rewrites the fix-up to direct, so we've lost the pre-stub, and the fix-up is now going to the native jitted code. So that's what it looked like traditionally when you jitter method. With tier compilation, it's left the pre-stub in, and that's where the counter is. So I think it's still 30, right? It counts if the method's been executed. I'm seeing some nods. So it counts at the moment if the method's executed 30 times, and then that considers that hot. I imagine over time it will be tweaked, the heuristics, to say, do something a bit more complex, or analyze it, I don't know. But at the moment it's 30 times. So there's a counter sitting there. So there's a bit of a cost for this tier compilation, but the point is at this point the method hasn't been called enough to make it worthwhile on the hot path. So we're still calling into native code, but it's just going by an extra level in direction to allow us to do the counting. Once the counting's finished and it's said, right, this is we should optimize this, we end up very similar to the first situation. We're now pointing at the optimized native code. The JIT has had a second go. It actually puts the method on a queue, and it does it in the background so it doesn't block the execution of the code. And we still have the original one hanging around, if you like, the original native code. And there's scenarios we'll talk about in a second that cover that. So that's what's happening under the hood with tier compilation. And yeah, if you're using .NET Core 3, this will be happening even if you don't realize it. And there's more work planned. So just as a final thing to talk about, it's part of a bigger strategy called code versioning. That actually, at the moment, there's only one use of it, which is tier compilation. But the idea is down the line, the JIT might have a second go, or a third go, or subsequent goes. It might say, actually, I know now more about the state of the program that's been running for a while. I know enough to have another go at optimizing this method. I could do something different. So it builds up a tree where you have the original ones. Regit is something you can do. People who work on profiling APIs will recognize regit, where you can actually provide a different version of IL for a method if you hook into that. You have the generics going on there with the different types. But the idea is that it could say, you know what, for int, I'm going to do a high JIT optimization for the int version of the generic method, but not the string one. So there's lots of things down the line that can make possible. So this is flashing at me to say my time's up. So that is me. There's some resources if you're interested in finding this stuff out for yourself. I've done a sort of walkthrough of how you can learn about it, explore it, tools that help you, other presentations from other people covering it. The Book of the Runtime is always a great place to start. But that's it from me. Thank you.
Thank you very much, ladies and gentlemen. Matt, Warren, Reagan. Thank you.